Hello everyone, this is TSS Zindabad and today we are going to discuss the Leetcode daily challenge. The problem is maximum difference between node and ancestor. So let's jump into the problem statement. Given the root of a binary tree, find the maximum value v for which there exist different nodes a and b where v is equals to absolute difference between the value of a and the value of b and a is an ancestor of b. A node is an ancestor of b if either any child of a is equal to b or any child of a is an ancestor of b. Okay, so after reading the problem statement, what I understand is that I first of all, if this is the tree that has been given to me, right, then here what I need to do is I need to figure out the maximum value, which would be the absolute difference between two nodes. And now these two nodes have a particular relationship. What is the relationship between these two nodes? That if I have a node A and a node B, then the node A needs to be an ancestor of node B. What is an ancestor? It is mentioned right here. And I'll explain you this with the help of this given diagram. For example, we know that we have a root pointer, right? So 1 here is the root. One's child is 2. One's right child is 2. 2's right child is 0. 0's left child is 3. This is something we all know. Ancestors are the parents of the parents, right? For example, I can say that 1 is the ancestor of 0 because it is because 0 is the child of its child. It is very similar to how family works. For example, your father and you, right? So your grandfather is your ancestor, right? This is your ancestor. So similarly, in tree hierarchical data structure, this is the very similar thing. So I hope you understand what is the ancestor and you can use this definition further. We'll be using this definition further for solving this problem statement. Now we've understood the problem statement and I need to understand that what will be the approach for this problem. So let's figure out what can be the approach to solve this problem. Now when I say I need to give you the maximum value which is mentioned here in the question, I need to understand that there can be different ancestors for a particular node, right? Now, when I say that, what do I mean is, let's quickly copy paste this image here again, right? So, if this is the node in consideration, let us say 2, right? This is the node in consideration, then the ancestor of 2 is 1, right? If 0 is in consideration, then we say that 2 is the parent, so it is also an ancestor. 1 is the parent of 2, which is the parent of 0, so it is also an ancestor. Similarly, if I talk about 3, 3 has 0, 2, 1, all of them as its ancestors. And when you talk about all of as its ancestors. So when I talk about 1, as 1 is the root node, it does not have any ancestor, right? So I figured out one thing that I can see something like for a particular node, I have to figure out all its ancestors and figure out the difference. Only then I'll be able to solve this question. So when I talk about going to each node and doing something on it, the first thought that comes into my head is recursion. When you have to repeat the thing, when you have to repeat what is already done again and again, right? So I have understood this one fact that for this problem, I will be using recursion to solve it and the concept of ancestors. So, okay, this is done and we understand that we have to do this. But how are we going to do it? And what is a basic thing that we need to take care of? So, as it was mentioned here, that V is the absolute difference between the value of A and B. I'll quickly write it here. What is V? V is the absolute difference between whatever is the value of the ancestor and the value of the node, right? So whenever we talk about difference, for example, I'm saying A minus B and there is a modulus. We all know anything inside this modulus will convert it into positive. So we do not have to worry about it being negative. We can simply move forward with it. So now what happens is, I know one thing, that if I want to maximize this, then in order to achieve this, I can have either A as maximum value, which is there in the tree, and is the ancestor of node B. This is the first thing that I can do. When I maximize this, I would want this to be the minimum value. I know that if I minus the minimum value from the maximum value, only then whatever the answer I get will be the maximum value. This is the first thing that we have to do. But as we know this one thing here, that the second thing I can see is, because we have this absolute sign, right? Because in the given question, absolute is given to us, we can say that we can even have a vice versa situation too. Now, what is vice versa? That means A, which is the ancestor, can have a minimum value and be the ancestor of B node, and the B node can be the maximum value. So this is the key concept of this problem. So what have I established so far? Let's quickly write it down here, that we will be using recursion because I see that I need to figure out the V value, that will be the maximum value, maximum difference between the A val and the B val, where A is the ancestor of B node, right? Second thing that I know is, for making it maximum, I'll be using the above two conditions. That is, if I want to have a mean B maximum, which is the absolute of A val minus B val, then I can have two cases. The first case being that the A val is the maximum value in the tree. So A val is the maximum value in the tree and ancestor of B node. And the second case, and the second part of the first case is that the B val is the minimum value in the tree, right? And is related to the node A. Similarly, the vice versa situation comes for case 2, wherein I'll say the A val can be the minimum value in the tree and an ancestor to the node B, and the B val can be the maximum value and be related to the node A. So I have figured out this is something that I need to achieve while I'm solving my question. So this is the approach I'll be following. Now let's quickly do a dry run before we jump into coding this. So let's quickly take an example here. So let us suppose this is the tree in consideration and I need to do what I've written above here, right? So to perform this, I hope it is still visible to all of you. So what I'll do is, I have been given this 8 as the root and I need to figure out, say, V, that should be the maximum value, and I have already explained the condition in detail. So what I'll do is, I'll have something like a main function, right? In the main function, what I can do is, when I talk about recursion, it is very important to understand how recursion works, right? So basically, recursion says you figure out the base case and I'll do the rest of the work, right? So figure out the base case and I'll do the rest of the work. So figuring out the base case means that let us assume that 8 was the maximum value, or say this is the root, this is the only root that will give me the answer. Let us suppose this, right? That this is the only root that can possibly give me answer, and there is no other root, just for simplifying the concept, right? So what I can do is, this is the left part of the tree, right? And this is the right part of the tree. So what I can do is, if I can figure out the minimum in the whole tree and the maximum in the whole tree. So that means if 8 is only in consideration, if the node 8 is only in consideration, and if I can figure out the minimum in the left part and the right part and the maximum, then I can solve this question, because this will again lead to solving this condition. So I can see that in the given tree, the minimum value comes out to be 1 and the maximum value comes out to be 40. So what I can do is, I can simply keep a certain variable. Let us suppose that is the final answer, right? And I will simply keep a maximum in which whatever I am considering that this is the node that will always give me the answer, right? I am assuming it here. So I'll say if the root val minus whatever is the minimum and whatever was already the final answer, we can initialize it using anything that's very small, 1e9. I generally prefer using this rather than int max or int min because of integer overflow. So it is always better to use this. And similarly, I can have one more condition in which I'll say the final answer is equals to the maximum root val minus whatever is my maxi and whatever was my final answer. So in this way, considering that only 8 could give me the answer, this should work fine. But when I talk about, it is not important that always the root node will give me the right answer or not, right? So for that, I will even traverse further the left part and the right part. The other major thing that you guys always need to take care of when I talked about maxi and mini, a lot of you would have thought, ye aaya kahan se? How are we getting this, right? This is very important to understand, that how are we getting minimum and maximum. So for that, we can simply have something like a find function, right? And in the find function, I'm not doing something rocket science, and I will simply pass the root, and I can have any of breadth first search or depth first search traversals to find the minimum and the maximum in the given tree structure that I will be given, right? And after that, for example, this function was, let us suppose it was something like solve. So I can further call it that if there is the left child of root, then we can call the solve function. And similarly, it will update the final answer. And if there is a right child, we'll call the solve function again. I hope this should be clear to you, right? Now let's quickly use this mini code structure that we've created and have a quick dry run for this image here. I'll copy paste the image so that we get a fresh image here. Okay, I hope the code is also visible to you. Okay, so now what I'll do is, I'll say, okay, I am following this above code structure, right? So the first thing it is asking me to do is that you need to find me the maximum and the minimum considering the root. So I'll be like, okay, I am here on my root and the find function is being, okay. So the find function is something that is returning me the minimum and maximum. How it can do this is, I can simply write the structure here a little bit again for your convenience, right? That, for example, you are using the pre-order in DFS. So pre-order in DFS says that first work on the root, then go to the left part, then go to the right part. So here it will directly say that if the root val, it is greater than maximum, then update the maximum. And similarly, if the root val is less than the minimum, update the minimum, right? And then follow the simple pre-order traversal, which says you first go to the left and then you go to the right. Okay. And obviously, when you have to add the if condition here so that you do not get into a runtime error. So we will be doing that when we'll be coding this up. So for the part of dry run, what I'll say is, okay, I'm on 8, right? So the first function call happened. I was at 8, and let us assume initially my maxi was minus 1e9 and my mini was 1e9, right? So this is something that has been sent to the function, and what it will do is it will traverse the whole tree and it will update these values. After updating these values, I'll have the maxi as 14, right? As you can see in the tree, that I'll have the maxi as 14 and I'll have the mini as 1. After doing this, I can have a final answer, and it is suppose I'm again initializing my final answer as minus 1e9. I'll come to these two statements. Now, in these two statements, what happens is it will say that let's calculate it. The root val was 8. So we'll say 8 minus 14, and we're taking an absolute value. And why this will always work is because we are moving in depth first search traversal method, right? So this node will always be the ancestor of the node that is below it, right? So now what we see is we get 6. Similarly, if I say 8 minus 1, it is 7. And accordingly, first of all, this becomes, because we did it with mini, so it becomes 7. The next time we had 6, it will not get updated. It remains the same. Now I'll go to this part of my code wherein I'll be reusing this function, the given function, and I'll be calling a recursive function for it, right? And that would be for the left part. Now, guys, you really need to understand that the understanding this code is really important, because first of all, we have figured out that only if 8 could give me the answer, then this works. But if there is something like another node somewhere that can give me the answer, that's a better or maximum answer, so you have to even work with the nodes that are below it, right? So what I'll do is I'll say now consider that this is the tree in consideration only, because I have passed my main function this. So now this becomes the root. Okay, so this was the first part. In the second part, now this is the root again. The find function will be called. When the find function is called, we'll simply say now it is 3, and we already have the maxi and the minimum value, but it will not be 14 and 1. Why? Because if you know how recursion works, as the whole function is called again, so maxi and mini gets reset to minus 1e9, 1e9 respectively. So I'll pass it. Now, what my find function here will do is, my find function would simply figure out what is the maximum and the minimum value here. So it will say that what I can see is this is the maxi and this is the mini, right? It will say I can see that the minimum value is 1 and the maximum value is 7. So after this is computed, I'll come again to the updating the final answer, and it would be 3 minus 7 and 3 minus 1. The answer is 4. The answer is 2. None of them being greater than final answer, it remains the same. Now after that, what I'll do is I have figured out the root left part, right? I again come here. So when you again come here, now your tree gets further shrink. So when I talk about further shrinking, it will say, okay, 3, you were in consideration. This was the node in consideration. So you'll say, do you have a left child? It will say, yes, I have a left child. So now our consideration tree is only this part. So what happens is, again, the code is run, and what I'll do is, we'll say find the root in consideration is 1, the maximum is 1e9, the minimum is 1, minus 1e9 was the maximum, minimum was 1e9, and after figuring it out using the find function, I can see that maximum and minimum becomes 1 again. Then we'll be computing the final answer. We'll say 1 minus 1, 1 minus 1. It will give me 0. As these values are not greater than whatever is stored in the final answer, it does not get updated. So then again, I'll come to this section of my code, the if part, wherein I'm calling the solve function again, the main function again. So it will say, do you have a left? It will say, no, I do not have a left. So it will simply say that, okay, if you do not have a left, then we'll not move here. We'll say, do you have a right? It will say, no, I do not have a right. So we'll move back. We'll simply return. So when we return, we had a recursion stack space, right? For all those people who do not know what is a recursion stack space, basically whenever the recursive calls are being made, that is why I was numbering all of them, so that first we have 8 here, then we have 3 here, then we called 1. So 1 completed, exhausted all of these statements, it gets popped out because it does not have any more children to go to. We return back to the node it came from. So now we are here, and 3 said, okay, for me, you guys have solved me till here. If you guys remember, why did we solve for this part was because we were here when we were dealing with the node 3 in the tree, right? It will say, okay, this line has been computed. Now go to this line. Now we'll say that, okay, 3, do you have a right? It will say yes. I'll say, okay. So now my tree in consideration changes. My tree in consideration becomes this portion. So when I am here, the recursion is again called, and as 1 is popped out, I'll put 6 up there. So now a find function for 6 happens, right? I'll say find 6 minus E9, 1 E9, right? And what I'll say is, okay, find me the maximum and the minimum here. So it says the maximum is 7 and the minimum is 4. So 6 minus 7 is 1 and 6 minus 4 is 2. But none of them being greater than what is stored in the final answer. In the final answer, we had 7. So it is still not updated. So after that, we move to this portion wherein we are calling the function again. And similarly, it will go to its left. That is the fourth part, the fourth node, I'm sorry, right? So it will come here. Now this becomes my tree in consideration. So similarly, all of the tree gets worked upon and we get the final answer. I hope this dry run would have helped you to understand how it is actually working. Now let's quickly code this problem and see if this approach works fine, or is there any little modification we might require. Okay, so this is the problem that we have just discussed. Now, according to what we discussed, what we'll do is we can simply say that if there is no root, we can return that there is 0 difference. The first thing. The second thing that we discussed in our code was that it is very important, first of all, to work for the base. What is the base? That is the root itself. So what I'll say is, I'll say that I'll use a find function. I'll give it root. I'll give it maxi and mini. So let's quickly create maxi and mini here. Let's keep maxi as minus 1e9 and mini as 1e9. And I'll give it to my find function. My find function would be a void function in which I can have any traversal, any DFS traversal. For the time being, I am going with the pre-order traversal that I've already told you. It follows the order root, left, and then right. So what I'll say is that suppose there is no root, you simply return in that case. Else, as I've told you, that we're working in pre-order traversal. So I'll say that if the root val is greater than maxi, so update maxi to root val. If root val is less than mini, then mini is equals to root val. And then I'll simply do the pre-order traversal, in which I'll say that if there is a left child for the root, then in that case, simply go to the left child, right? And if there is a right child for the root, then go to the right child. So this is done here. We're done with the find function. After finding this, what I'll do is I'll say let's have a final answer variable, which is storing what I have to finally return. And as it needs to be the maximum value, so I'm initializing it with a minimum value, that is -1e9. I'll simply say that final answer is equals to the maximum of final answer, comma, the absolute difference between whatever was the root's val minus whatever is maxi. And similarly, I can just copy paste statement here and I'll change maxi to mini. After this, now what we were doing was, after computing this, we have worked with the base. Now I would want to call recursion that, okay, I have told you how you have to do it. Now do it for the leftover part. That means the left child and the right child. That means the left subtree and the right subtree. So I'll simply say that if root has a left, in that case, what you need to do is you simply need to compute that. You can simply use this statement here, that, and we can modify this. Final answer is maximum final answer, and here we'll change this to the name of the function, that is maximum ancestor difference, and we'll pass it the root's left child, and similarly we'll do it for the right child. We'll say that if there is a right child for the root, then compute me the final answer. That would be the maximum difference between the value of A node and B node, and A being the ancestor of B, and we'll simply return the final answer here. I think we're good to go. Let's see. Okay, it works fine. Let's submit the code. Yes. So this is the solution. Now let's quickly see the time complexity and the space complexity for the problem. Okay, so this is the code that we have worked on, and as you can see that in this part we are calling the recursive function, that is the find function, and in the find function I'm implementing something like DFS. So DFS is going to every node in that particular tree, right? As you saw that we were giving different trees one by one, right? While we were traversing different tree structures. So at worst time complexity, it would be O of n, because it would be visiting all the nodes, right? So n is the number of nodes in the tree. Then we can see that we're simply having certain variables that does not add into it. And here again, we are calling the recursive function, wherein I'm recomputing this. So this is again O of n. Therefore, the time complexity overall is again O of n, where n is the number of nodes in the tree. Talking about the space complexity, as in this case, we are not explicitly storing anything except for a variable, but we will still have O of h type space complexity. That is because of recursion stack space. Recursive stack space. That is because of recursive stack space. So the recursive stack space, in that, what we have is, as you saw, that everything was getting piled up and we were calling this function, right? So it was a stack was created. So in the worst time complexity, if we get a skewed tree, right? I have already told you in my previous videos also, skewed tree is the one which is not balanced, right? So in that case, the time complexity, the space complexity can be up to O of n, because in that case, I'll be storing, for example, if I something like 1, 2, 3, 4, 4 has 5 and 6. So what happens in this case is, I'll quickly tell you here that first we have computed everything for 1. We reached this statement and it says, do you have a left? It will say yes. So before completing this section of the code, I'll simply start working with the left node, and 1 remains in my recursive stack space, right? So it remains in my stack space. Then again for 2, I've computed all of it. I've reached again here. I'll say, do you have a left? It will say, yes, I do have a left. We'll again add 3 here. We'll compute 3. We'll ask, do you have a left child? Yes, added into the stack space. We'll say 5. Yes, added into the stack space. Finally, when 5 gets computed, at this point, what do you see? This is the almost all the nodes have been added in the recursion stack space. So that is why the worst time complexity is O of n, and the space complexity is also O of n. In the best case scenario, it would be O of h, where h is the height of the tree. But the time complexity remains the same, that is O of n. Only the space complexity in terms of the best is height of tree. Thank you so much for viewing the video till the end. Please like, share, and subscribe. Thank you.